Hello students, this is lecture 21 of MTH 201. In the last lecture, we discussed double integral over elementary regions, mean value theorem for integrals and triple integral. In today's lecture, we are going to discuss a very important tool in integration which is called change of variables. It's something that you have seen in one variable calculus. And change of variables play a key role in simplifying the process of integration. For example, if you want to integrate this function 2x by x square plus 1 over the limit 0 to 1 of x, you can't do it directly. So what you do is you make some change of variable. There are several options. One of them is taking y equal to the denominator, which is x square plus 1. Then dy will become 2x dx. And if you substitute this in the integral, this is what you get. And the limits now are limits of y, right? So when x is 0, y is 1. When x is 1, y is 2. So that those are the limits, and then you integrate, right? So the simple change of variable actually simplified the integration process quite a lot. So we are going to talk about three primary change of variables. Uh, First is polar coordinates, which is for two variables. So when you have R2 or the plane, then this is what you do. So for integration of functions of two variables, we make use of change of rectangular coordinates, right? X, y are called rectangular coordinates to polar coordinates r, comma, theta. We'll come to all this. I'm just telling you what we are going to do in this lecture. Then for integration of functions of three variables, we make use of change of rectangular coordinates x, y and z to cylindrical coordinates r, theta and z and to spherical coordinates r, theta and phi. Okay. So these are three special kinds of change of coordinates or change of variables, but we are going to talk about a general notion of change of variables as well. So let us first talk about change to polar coordinates. So polar coordinates are r, comma theta, right? And they are related with rectangular coordinates x, comma y as follows. So x is equal to r cos theta and y is equal to r sin theta, where r is any non-negative real number, r is greater than or equal to 0 and theta lies between 0 and 2 pi. Okay, 0 included, 2 pi excluded. So how are these r and theta obtained? So if you look at this picture, this is in rectangular coordinates, right? X-axis, y-axis. So if I have a point xy in the rectangular coordinates, then r is nothing but the distance of that point from the origin. Okay. And what is theta? Theta is the angle that this line joining origin and xy makes with the positive x-axis. Okay. So you can see that if you are in the first quadrant, then theta is less than or equal to pi by 2 and pi by 2 when you are on the y-axis on the positive side. When you are here in the second quadrant, theta is from pi by 2 to pi, then pi to 3 pi by 2 and finally 3 pi by 2 to 2 pi. And at 2 pi, you are back to the positive x-axis. Therefore, 2 pi is not included. It's same as 0. Okay. And then, of course, you know that because cos theta, sin theta are both 2 pi periodic, things will repeat themselves after 2 pi. So, therefore, we restrict our limit to this thing. Okay. So, how do you compute x? X is this distance. So if this is r, this is theta, this is r cos theta and this height which is y is r sin theta. Okay. So this is what happens when you make these change of variables. So by substituting xy with r theta, which is the polar coordinates, the double integral of fxy over a region D in R2 becomes, so this double integral becomes, so you replace x by r cos theta, y by r sin theta, and dx dy by r dr d theta, where d star, so now the integration limits have to be for r theta, right? So d star is the corresponding region in the r theta plane. So whatever happens to d, when you make these change of variables, that is called d star. We will come to the rationale behind this formula later. So but first let us look at a few examples. Okay. So keep this picture in mind. This is of course for a point which is in the first quadrant, but it's equally applicable for any point. So if you are given polar coordinates, let's say, how do you compute rectangular coordinates? By taking x to be r cos theta and y to be r sin theta, right? So now think about what r is. So if you square both equations and add, you get x square plus y square equal to r square, right? And what is theta? You divide one equation by the other, you get tan theta is equal to y by x. So theta is tan inverse y by x. That also follows from this picture. Okay. So let us look at this first example. Suppose x is 1 and y is 1. Then r is square root of x square plus y square, right? Which is square root 2. And theta is tan inverse of y by x, which comes out to be tan inverse 1. Now in 0 to 2 pi by 4, there are 2 points where one value is obtained. But we will take pi by 4 because your point is in the first quadrant, right? So this angle can't be more than pi by 2. Therefore, we have chosen it to be pi by 4. Suppose I take a point a minus 1, which is in the third quadrant, right? So again, r is square root 2, theta is tan inverse 1. But now tan inverse 1, you will take the other value between 0 to 2 pi 4, which is in the third quadrant, right? Meaning which is between pi and 3 pi by 2, which is pi plus pi by 4, right? Now, suppose D is the triangular region bounded by the lines y equal to x, y equal to minus x, and y equal to 4, right? So the question is, if you convert this into polar coordinates, what happens? So I have not given you the picture here. I would like you to draw this picture in R2, the region D. This region is actually described as minus y less than or equal to x less than or equal to y, right? Because it's bounded by these two lines. And y lies between 0 to 4. Okay, so you can check that this is indeed the region. So if you convert it into polar coordinates, y is r sine theta, x is r cos theta, right? So if you put it in this equation, in this inequality, you get minus r sine theta less than or equal to r cos theta less than or equal to r sine theta, and y is r sine theta, so 0 is less than or equal to r sine theta is less than or equal to 4. So if you rearrange the terms here, you divide everything by sine theta, you get this, right? And the second equation, if you divide by sine theta, you get this, right? And this can also be written as, now cot theta lies between minus 1 and 1, therefore theta lies between pi by 4 and pi minus pi by 4, right? Those are the values when cot theta takes the value minus 1 and 1. And this range is happening because the triangle lies in the first and the second quadrant. So I would like you to draw this picture and see for yourself that this is indeed the case. Okay. And R of course lies between 0 and 4 cosec theta. Okay. So now let us look at this example where you are integrating this function log of x square plus y square over the region which is in the first quadrant lying between the circles this and this. Okay. So this is the picture. So this is the region D, right? It lies between the circles of radius 1 and 2 in the first quadrant, right? So we want to convert it into polar coordinates. So in terms of polar coordinates, what is this region? Now R is the distance from the origin, right? So if you are in this shaded region, then your distance is from 1 to 2, right? Because you are within these circles, right? And what is theta? Theta goes from 0 to pi by 2, right? This is your range. So it's a very simple description in r theta coordinates. And if you plot it in r theta coordinates, you just get a rectangle, right? Because if this is your r axis, this is your theta axis, r goes from 1 to 2 and theta goes from 0 to pi by 2. So this is the rectangle that comes out when you change your function coordinates to polar coordinates. So therefore the integral becomes, so x is replaced by r cos theta, y is replaced by r sin theta. So x square plus y square is r square. A region is d star, which is this rectangle, and dx dy is replaced by r dr d theta. So now you have something very nice, right? Now you know what the limits are. Because what are these limits? These limits are nothing but the limits of these rectangle, right? So theta goes from 0 to pi by 2 and r goes from 1 to 2. And then of course log r square 2 comes out. 2 is here. Log r dr d theta. Now it's just a simple double integral which you can solve by integration by parts, right? So I have given the calculations. I will not go through the calculations. So this, from this step to this step, I have used integration by parts. Okay. So you can go over these calculations yourself. Okay. Let us look at why you have this formula. Okay. So if you look at, so what is r? R is the distance from the origin of the point and theta is the angle, right? So here what I have done is I have gone from r to r plus dr. Okay, so dr is the infinitesimal change in r and d theta is the infinitesimal change in d theta, in theta, right? So if you look at what happens to this additional region, it's actually this arc region, right? This shaded region. The angle is d theta and this length is dr, right? So which means that what is the length of this arc? It's r times the angle, right? Which is r d theta because d theta is the angle and this side is dr. So it's an arc region but it is like a rectangle, right? Whose one side is dr and other side is r d theta. So what is the area of this rectangle? It's r d theta dr, which is this extra term. So what happens is this rectangle, shaded rectangle, is the image of the infinitesimal rectangle that you have in the rectangular coordinates, right? So the left hand side integral can be thought of as summing the values of f over infinitesimal rectangles with sides dx dy and therefore the area is dx times dy. Right? So if you remember double integral, we had divided our rectangular region into smaller regions and then added up the integral. So it's the same concept. Now such a rectangle is transformed into a region in polar coordinates as shown in this figure, and the area of this region is r dr d theta as I just described. So therefore in the new coordinates we can think of double integral as summing the values of f over the infinitesimal regions with area r dr d theta, and therefore we obtain this formula. Okay. It will take a while for you to understand what's going on, but the idea is you have to see how a rectangle in rectangular coordinates of sides dx dy transform to a region with sides dr d theta in the polar coordinates. Okay. So now we will come to three variables, and the first change of coordinates is called cylindrical coordinate, change to cylindrical coordinates. So what are these coordinates? They are very close to polar coordinates, and cylindrical coordinates are r, theta and z. So z is retained and x and y are replaced by r cos theta and r sin theta. So it's the same thing. In the xy plane you are changing to polar coordinates and the z coordinate remains as it is. Okay. And of course here also r can take any value which is greater than or equal to 0, and theta lies between 0 and 2 pi. So pictorially this is what is the picture. In xy coordinates r is the distance of the point. Which point now? Projection of xyz onto the xy plane, which is x comma y comma 0. So what is the distance of 0 0 0 and x y 0? It's nothing but x square plus y square square root, right? So that is your r. Theta is the angle that this line joining 0 0 0 and xy 0 makes with the positive x axis, which is theta, and z is of course the height. So now it's the same idea. If you have a box here of sides dx, dy, dz, what happens to that box when you take it to cylindrical coordinates? So this is the picture. So r to r plus dr, which is the infinitesimal change in r, z goes to z plus dz, which is the infinitesimal change in z, and theta goes to theta plus d theta, which is the infinitesimal change in theta. So this arc region is of length r d theta, r times the angle, height is dz, and this side is dr. So if you multiply all of them, this box has volume r dr d theta dz, right? So that is what you get here. Okay. So a box of sides dx, dy, dz converts to such a box with these sides. And the integration now is over the region W star, which is how W transforms as a region in the cylindrical coordinates. Okay. Let us look at a few examples. So given cylindrical coordinates, how do you compute rectangular coordinates? By these equations. If x is 1, y is 1 and z is 5, then of course r is this, theta is this, and which is pi by 4 because 1 1 lies in the first quadrant. I have just transported the same example that we did in polar by taking some value of z. So it has no implication to r and theta because they are solely in terms of x and y. Z has no role to play. Now, this last bit is important. In rectangular coordinates, if I look at this equation, remember in R3, So this equation is the equation of cylinder with z-axis as its axis of symmetry, right? If you draw this cylinder, this is what you get. So in cylindrical coordinates, what is the equation? It is nothing but what is x square plus y square? It is r square. So r square is equal to c square, or r is equal to c. So in cylindrical coordinates, this complicated equation takes a very simple form in terms of r alone, because z is arbitrary, theta is arbitrary. When you look at this cylinder which has z axis as the axis of symmetry, then r is constant, right? The distance from the origin remains constant. Okay. So let us now look at another example. So evaluate this triple integral where W is the cylindrical region given by this. Now what is this region? X square plus y square is less than or equal to 1. So it is what is there inside the cylinder, right, of radius 1. And z goes from minus 1 to 1. So it goes from minus 1 to 1. So this is this cylindrical piece over which you have to integrate. Okay. So in terms of cylindrical coordinates, what is r? R goes from 0 to 1, right? That's the maximum you can go. Theta takes any possible value which is 0 to 2 pi, and z goes from minus 1 to 1, which is what I have written here. So now in cylindrical coordinates, this cylindrical region has actually become a box, right? So this is r, this is theta, this is z. R goes from 0 to 1, theta goes from 0 to 2 pi, and z goes from minus 1 to 1. So this box is what you get as W star. So if you look at the integration, you replace x by r cos theta, y by r sin theta, z remains as it is. This is what you get. And then you have an additional r which comes from change of variables, and you integrate over the new region. But this is nothing but integrating over a box, right? So this is what you get. Now this integration is easy because you have z cube here, and you are integrating z from minus 1 to 1, right? Now z is an odd function, right? Z cube is an odd function. So when you integrate from minus 1 to 1, you get no contribution, you get 0. And there's no other term of z, so it's actually equal to 0. So W is symmetric about the xy plane and the integrand is an odd function of z. Hence, without computing, we can conclude that integral is 0. So in this particular example, you need not even have to go through all these jargon of converting to cylindrical coordinates, because you look at the integrand, it's an odd function of z and your region is symmetric about z, right? So this integral has to be 0. There is no other choice. Okay. Now let us look at the third kind of change of variables, which is called change to spherical coordinates. So now spherical coordinates are also change of variables of R3, rectangular coordinates x, y, z, and they are rho, theta and phi. And this is the relationship. X is equal to rho cos theta sin phi, y is equal to rho sin theta sin phi, and z is equal to rho cos phi, where rho is greater than or equal to 0, theta goes from 0 to pi, and phi goes from 0 to pi. Okay. Let us understand how do you geometrically see rho, theta and phi. So this is R3, rectangular coordinates, x axis, y axis, z axis. Take a point x, y, z. Take the projection. Okay. So what is this point here on the xy plane? It's x, y, 0. Okay. Now what is rho? Rho is the distance of this point xyz from the origin. So rho square is equal to x square plus y square plus z square, right? Okay. What is phi? You take this line which joins origin and xyz and you look at the angle between the positive z axis and this line. This is phi. Okay. So if this is equal to phi and this height is z, what should z be? It should be rho cos phi, right? Because this is also phi. So this height is rho cos phi. And what is r, which is the distance of origin to this projection? It's rho sin phi, right? So r is equal to rho sin phi. So if this angle is theta, which is like polar coordinates, then x has to be rho sin phi, which is this r times cos phi, and y coordinate should be rho sin phi times sin theta, right, which is also like polar coordinates. So remember here that r is equal to rho sin phi, right, because that is the, if you look at this shaded triangle, this is projection, so this is perpendicular, and if this is rho, which is the hypotenuse, and this angle is phi, then r is equal to rho sin phi. Okay. Now in this case, the change of variable is a little bit complex. Here you write x to be this, y to be this, and z to be this. And you have this additional term which is rho square sin phi. Okay. And w star is the corresponding region in the new coordinates. How do you get this? So you do the same thing. You have theta, the infinitesimal change in theta is d theta, infinitesimal change in rho is d rho, and infinitesimal change in phi is d phi. So this, whatever box you have of sides dx, dy, dz goes to this region of sides r dr d theta, d rho and rho d phi, but r is rho sin phi. So you get a box whose sides are d rho, rho d phi and rho sin phi d theta. If you multiply all of this, you get rho square sin phi d rho d theta d phi. That is the rationale behind this extra term. Okay. Let us look at a few examples. So given spherical coordinates rho, theta and phi, rectangular coordinates x, y, z are obtained using these equations. If x is 1, y is 1 and z is 5, then rho is square root of x square plus y square plus z square, right, which is square root 27. Theta is tan inverse y by x, which is pi by 4, because again 1 lies in the first quadrant. And phi, remember, if you look at this, z by rho is cos phi, right? So phi is cos inverse z by rho, which is cos inverse 5 by square root 27. But you have to take appropriate theta, phi, right? Now phi is this angle which this point, this line makes with the positive z axis. So if this point is above the xy plane, then phi has to be less than pi by 2. So that is the value that you will take. Okay. Now if z is positive, meaning if you are above the xy plane, then phi lies between 0 and pi by 2, right? And if z is 0, that means you are on the xy plane, then this point is here, right? That means this phi is equal to pi by 2. And if you are below the xy plane, if z is negative, then phi is between pi by 2 and pi, right? So I would like you to pause for a minute here and figure out these things from the picture. Remember, phi is the angle that this line joining origin and xyz makes with the positive z-axis. Okay, so it's like whether you are above the floor or whether you are below the floor. And if x and y are both 0, that means you are on the z-axis. And if z is positive, then phi is 0, right? Because this angle is just 0, you are here. And if z is negative, you are on the bottom and phi is equal to pi, right? You are here down in the bottom. In case of cylindrical or spherical coordinates, theta can lie in 0 to pi or in minus pi pi, right? Same with polar coordinates also. And the idea is that you're 2 pi periodic, right? These functions cos theta, sin theta are 2 pi periodic. So you can shift the entire interval to 2 pi. It does not matter, right? Okay. Let us look at this example. So evaluate this triple integral where w is the unit ball, x square plus y square plus z square less than or equal to 1. So this shaded region is what you have. So in terms of spherical coordinates, it's a very nice region because now rho is the distance from origin to the point. So now the point can go from 0 to this side, this, right? Origin to this. So rho goes from 0 to 1. Theta can take any value from 0 to 2 pi and phi also can take any value from 0 to pi. So spherical name comes from the fact that when you have a sphere, it takes such a nice form, right? So spherical coordinates are naturally designed for giving coordinates to points in a sphere. So in rho, theta, phi or spherical coordinates, you get a box. Rho goes from 0 to 1, theta goes from 0 to 2 pi and phi goes from 0 to pi. So the integral becomes this. Remember the extra term rho square sine phi and x square plus y square plus z square is rho square. So you get this and then you can just integrate it, right? You write down the limits for rho, theta and phi, you integrate. So I'll not go into these things. Another example, I will quickly go over the region because integration is not so crucial here. So W is the portion of the cylinder x square plus y square less than or equal to 1 inside the sphere x square plus y square plus z square equal to 4. Okay. So this sphere is the region x square plus y square plus z square equal to 4, right? So radius is 2 and this cylinder is this cylinder, right, with radius 1. So you are looking at region which is lying inside the sphere, right, inside the cylinder. So this is the shaded region. So the integrand is even in all the variables x, y, z. So I am going to use symmetry argument to simplify some of the integration. And the region D is symmetric about the xy plane. I'm sorry, region W is symmetric about the xy plane, right? And also z-axis is its axis of symmetry. Hence, you can think of integrating this function only over this shaded region in the first octant. There are 8 octants, right, of R3. So just focus on the first octant where all x, y, z are positive. You integrate the function over that and you multiply the integral 8 times. Now, so in the xy plane, what is the region? It's x square plus y square less than or equal to 1, right? And z coordinate goes from this thing to this thing, right? Now the bottom part, what is z square? Equal to 4 minus x square minus y square, right? Because you are on the sphere. So z goes from 0 to this portion, which is square root 4 minus x square minus y square. And cylindrical coordinates are most appropriate here. And in terms of cylindrical coordinates r theta z, this region in the first octant corresponds to this region, right? Where z goes from 0 to 4 minus r square. R goes from 0 to 1 because that's the distance from the origin to the projection. And theta goes from 0 to pi by 2 because I'm just focusing on the first quadrant. So the integral becomes this, and you have this extra term r because of cylindrical coordinates, and these are your limits. Now here you have to notice one thing. So in all the other examples, all the three limits were constant limits, right? Because we were getting a box. In this case, we are not getting a box. In this particular example, your z depends on r. So therefore, you can't integrate the r variable before the z variable because there will be an extra r term then. So first you integrate over z, which has r term as one of the limits, and then you integrate over r. Okay, so the order of integration here is quite crucial. Okay, so now let us look at these few examples where spherical coordinates are useful. Okay, in these pictures. So the first figure is equation of a sphere in rectangular coordinates which has form x square plus y square plus z square equal to c, right? And in spherical coordinates, what is the equation? It's rho equal to c. Actually, rho equal to square root c, right? Because this will give you rho square. The equation of a half plane in rectangular coordinates, which is this plane, in rectangular coordinates is y equal to mx, right? Where x is either positive or negative depending upon where you are. So therefore in spherical coordinates the equation becomes y is equal to r sine theta, x is r cos theta, so tan theta becomes m, or tan theta is a constant where constant is tan inverse m, right? So that is the equation of half plane. Now equation of a cone in rectangular coordinates is m square z square equal to x square plus y square. We saw it in the case of when we were talking about quadric surfaces, and hence in spherical coordinates the equation is what is z? Z is rho cos theta and x square plus y square is rho square sine square theta. So you put everything here. But this takes you to m is equal to tan phi, right? Or phi is equal to c, where c is tan inverse m. So this is the equation of cone, and now in the third figure you have cone above the xy plane. Therefore this c, which is the angle phi, has to lie from 0 to pi by 2, and if it's below the xy plane then phi has to lie between pi by 2 and pi, right? So this last part we have already discussed about phi. Okay. Okay, so let us stop here.